Good afternoon, everyone, and welcome to another edition of our live astronomy series, bringing astronomy into your living room from my living room. I'm Justin Bartel, the astronomer at the Science Museum of Virginia, and I'm happy to be your guide for this trip through the universe. In case you're just joining us for the first time, a couple of notes about the show. This is part of an ongoing series, and the goal is to get to the edge of the universe before cabin fever really sets in. So we're going to make small steps along the way. Today, we're just going to focus on the outer solar system, so the gas giant planets. But as always, if you have questions or maybe requests for future shows, feel free to leave those in the comments. A couple of other notes. If you watched last week, welcome back. Good to see you again. As always, we need to thank Allianz Partners for being our sponsors for this series. For the rest of the show, we're going to be watching video that is produced using the same software that runs the dome at the Science Museum. It's planetarium software called Digistar 6. I can do some pretty cool stuff, so I'm going to be watching the show along with you, and I've got it on a second monitor off to the side here, so I may not really be watching the camera all that often. In fact, I am going to get things set up for you here so that you can see the same stuff that I am seeing. So we'll switch on over. Last week, we kind of finished up with a trip through the inner solar system. And there were a lot of great questions from you during the show. Actually, went back and read a few of them. I was able to answer some of them during the show. But see, I've still got a few messages in the inbox there. So let's take a look at a couple of other things that were said during the last show. Since we are doing an ongoing series, we're going to see a lot more in the coming weeks. A couple of your questions I'm going to leave in my inbox here. We'll get back to them later. Like, we had one question from Jennifer who asked how many stars are in our galaxy. Well, stay tuned. We're going to get out of the solar system and see the rest of the Milky Way before too long. Another great question came in from Julia, who wanted to ask how are planets made? Well, maybe just watch the rest of today's video, may get a hint about that one. This was probably my favorite question from all of last week, though, from Aiden. Where is Pluto now, and what really happened to it? Well, that is a big question. And of course, we can't really get out of our solar system without talking about Pluto. So it will certainly make an appearance. I think I've got it on the schedule for about 2 weeks from today. Let's see, I have another message here. Seems to be related. It is from the International Astronomical Union. They say a planet in the solar system this doesn't really look like a question, but they are saying it's in orbit around the sun. That makes sense. It is in something called hydrostatic equilibrium, or it's round. All right, that's fair. And then it has cleared the neighborhood around its orbit. Well, okay, maybe that'll be important later on. Let's see, some other good questions related to topics that we saw last week and won't really revisit today. Janelle asked if there was life on the moon, and not any that's native to the moon as far as we know. Of course, temporarily there were astronauts on the moon during the Apollo program. There's also another kind of funny story. There's a spacecraft that was sent to the moon, last year, and it came out later after it unfortunately suffered a crash landing that they had put a whole bunch of tardigrades on that spacecraft. So they're like little microscopic things. They're nicknamed water bears, and so thousands of those are on the moon now, and they may have survived. They're incredibly hardy. We've sent them to the space station before. We know they survived that journey, and so maybe they're still on the moon too. Maybe we'll go retrieve them someday. One other moon question before we dive into the outer solar system today. Actually, 2 moon questions, but they were related. Both Elliot and Alice wanted to know why the moon changes shape in the sky, why it goes through phases when we see it here on Earth. That was a popular enough question that I thought we'd take a quick look at it. So let's just take a look at the moon here. We'll zoom out from the Earth just a little bit, and let's make things a little bit bigger so they're a little bit easier to see. So I've got a giant moon going around the Earth. We talked a lot about sizes last week, so that's not quite right. But the reason the moon appears to change shape in our sky is because of some of the time periods we talked about last week. So it takes the Earth 1 year to get all the way around the sun, and then it takes the moon about 1 month to get around the Earth. And as we watched it, I made copies of the moon. So right now you can see the sun off in the distance, and we just see the nighttime side of the moon. But if we get a little bit closer to the Earth here, and try and stop before we land in the South Pacific, I'll shrink the Earth down so that you can see the moon in the background. And you can see that, well, we've got a moon over there off to the side. It's a nice skinny little crescent. That's how we'd see it in the sky. But as we move through time, if we were to watch the moon, look forward about a week later, it'd be about a quarter of the way around its orbit. So I'm just going to keep rotating us around. And so now you see another copy of the moon on the screen. And that second one on the left side over here now looks much larger. It's a shape we call a gibbous. If we go a little farther around, I didn't make a copy of it at that time. But of course, you get a full moon when the moon is directly opposite the sun in our sky. And we go on around, you get another little gibbous, then another little skinny crescent that appears in the early morning sky. And then finally you get the moon lined up with the sun in the sky. It's actually up during the day. That's a new moon. But when the nighttime side of the moon is pointed our direction. So there you go, just the orbit of the moon, and it's 1 month period that it takes to get around the Earth that gives us those different phases. Figured that was worth taking a closer look at. But today, I promised you a slightly longer journey. We stuck to the inner solar system last week, just saw the planets out to Mars. And so let's get those back on the screen, see where we were before we take a look at where we are headed next. Let's get the planets' orbits up there. And since we talked about sizes a lot last week, I showed you how long it takes for the planets to rotate and get around the sun. Today seems like a good time to talk about distances just a little bit. Now, in astronomy, those can be pretty big. Space is really large. Things are really spread out. So measuring distances can be kind of tough, even here in our solar system. Take the Earth, for example. Its average distance from the sun is, well, pretty big. Today, it's about 152 million kilometers away from the sun, or about 93 million miles. Now, if we were going to do math with big numbers like that, I'd probably need a calculator. So astronomers' secret is they've defined a new way to measure distances, and the Earth is on average 1 astronomical unit away from the sun, a little bit farther away today, it just so happens. But 1 is much easier to remember, and then it's easier to do the math in the solar system too. Like Mars right now is about 1.5 astronomical units away from the sun, about 50% farther from the sun than we are. Now, by the end of the show today, when we travel all the way out to Neptune, we will cover a much larger distance. So to help us track it during the show, I'm going to put a little number down in the bottom right corner of your screen that shows how far we currently are from the sun in those astronomical units. Remember, you can just multiply that number by 93 million, get the number of miles. But by the time we get out to the orbit of Neptune, which is on average about 30 astronomical units from the sun, we will have covered about 3 billion miles. So it'll make it a little bit easier if we just use astronomical units. So that's what we'll do during the show and probably for the next couple of episodes. All right, so with that groundwork out of the way, let's actually go see the planets on our schedule today. So let's start with the closest gas giant to the sun, planet number 5 in our solar system. Let's go see Jupiter. Now, Jupiter is a pretty interesting planet. It is not just a gas giant, it is the largest planet in the entire solar system. In fact, I can add little models of all of the planets we saw last week onto your screen, and you see just how much larger Jupiter is. In fact, Jupiter is larger than all of the other planets in the solar system combined. You could grab the other 7 major planets, all of the moons too, mash them together into one giant ball, and Jupiter would still be bigger. Now, how did Jupiter get that large? Well, this goes all the way back to when Jupiter formed. We think Jupiter was the first planet to form in orbit around the Sun, and it probably happened pretty early on. The Sun seems to be about 4.5 billion years old, and it would have formed from a huge disk of dust and gas. The disk rotates around the young sun, and in places where the disk is a little bit thicker, gravity can take over, form a little clump that, can attract more stuff to it. It starts almost like a dust bunny forming under the couch, but just on a much larger scale. These dust bunnies get pretty big. Then when they get big enough that their gravity can start attracting more and more stuff around them, a little protoplanet can be born, and then it can grow into a planet. We think Jupiter started out as one of these little protoplanets, although it may have been the size of the Earth, or maybe a few times the size of the Earth. So its gravity was pretty strong. It kept pulling in more and more material. And this dust and gas was mostly simple ingredients, a lot of hydrogen and helium, water, ammonia, stuff like that out there too, but mostly those simple ingredients. And when you get a lot of those simple elements that are usually gases here on Earth together, they get squished together. So we think most of the interior of Jupiter is not a gas at all, even though we call it a gas giant. Inside Jupiter, this stuff is mostly fluids, or even, in the case of the hydrogen, metallic hydrogen. Now we're trying to sort out some of the details with the help of this spacecraft. The spacecraft is named Juno, and it's been here in orbit around Jupiter for a few years. Now it is investigating the inside of Jupiter, its interior structure, along with its magnetic field and things like that. Now I'm going to see if I can find Jupiter on the screen for you. We've actually traveled a small distance away from Jupiter, so it's kind of hard to find. I think that's it, though. You may have trouble recognizing it on your screen. So what do you say we get just a little bit closer? That's what Juno does every 53 days or so. Its orbit is very elliptical. It's really stretched out into an oval shape. So every couple of months, it gets much closer to Jupiter than it is today. And in fact, it's not going to be long until it makes its next close approach. Looking on my virtual calendar here, it looks like it's scheduled for early next week. Now, how close does Juno get at its closest approach? Well, I think we've got the answer on our screens now. It skims just a couple thousand miles above Jupiter's cloud tops. I've still got time slightly accelerated here. It doesn't go quite this fast, but it does go by the planet pretty quickly. And these really close approaches are incredibly useful. You get pretty pictures back of Jupiter, of course, but then the other science instruments help us see details of Jupiter's magnetic field. Most planets have a magnetic field. The Earth does. That's why compasses work here. We've got a north and south magnetic pole. You could use a compass on Jupiter too, but wouldn't always point to the same magnetic field. It's kind of spotty on Jupiter. And the close passes also allow Juno to give us some insight onto the planet's atmosphere. Its internal structure and its gravitational field. And so that has given us a little bit of insight into what the inside of Jupiter might look like today. And I'm going to try and show that to you. So I'm just going to split Jupiter in half here. And so the different colors here represent the different layers we think exist inside Jupiter, and it's similar in the other gas giants that we'll see today. So there is a really dense core, probably rocky and metallic ingredients, and then it kind of gets fuzzy inside Jupiter. Like some of these rocky materials, these minerals are kind of mixed in with the metallic hydrogen and the liquid helium that are in that thickest layer. And there's a darker blue layer out there getting closer to the outside of Jupiter that is mostly liquid hydrogen and liquid helium, and then just the outermost layer is truly gas. So that's kind of the picture that we're drawing today. But that kind of fuzzy interior structure was a little bit of a surprise. And so what planetary scientists think may have happened is that a long time ago, maybe early in Jupiter's formation, something hit it. Another one of these proto-planets, a baby planet in the solar system. And if it hit Jupiter's young core, it could have kind of broken it apart and gotten it mixed up with all the gas and dust that was gathering around it. So that may explain the kind of partially dissolved or partially mixed up inside of this planet. A pretty cool idea, and something that we could have only figured out with the help of the Juno spacecraft. But while we're here at Jupiter, let's look at some of the other things that gas giants do. Let's look at the atmosphere, the outermost layer, that gaseous layer that we can see when we just look at pictures of Jupiter or see it maybe through a telescope from the Earth. You see some different stripes going across the cloud tops here. And these are parts of Jupiter where the winds actually whip around the planet in different directions. Where these winds meet, you can get big storms, like the famous Great Red Spot that you see there, kind of front and center. That's a cyclone, kind of like the hurricanes that we get here on Earth. They work slightly differently here on Jupiter. And then, of course, this particular storm has been going for at least 150 years, maybe twice as long, maybe even longer. We've been able to see big storms like this on Jupiter for as long as we've been pointing telescopes at it, although in the early days it's not always clear if we were seeing the same storm each time. Now, to help you keep track of how these different regions are split up, I made a little cheat sheet over here on the nighttime side of Jupiter. These lighter regions are called zones, and the darker regions are called belts. And again, that's just where the wind is going around Jupiter in different directions. And sometimes the zones and belts kind of change size, and then sometimes they'll disappear entirely. So just like the weather on our planet is always changing, the weather on Jupiter is always changing too. We could get into a lot more detail on the atmosphere here, but then we have to get into a lot of fluid dynamics, which is really complicated. So let's just stick with celestial mechanics, and let's focus on some of the other things that are with Jupiter as it orbits the sun. Just like the Earth has a moon, and I don't think I mentioned it last week, but Mars has a couple of little moons too. Jupiter has moons, and you may have been able to pick out a couple of them on your screen already. If we get rotating around here, you'll see that there are a couple of other little dots on your screen that are kind of hanging out with the planet. And some of them are a little bit easier to pick out because they're a little bit bigger than all the rest. Jupiter has 4 really big moons. Now, we've known about them for over 400 years now. We call them the Galilean moons because Galileo was one of the first astronomers to see them. You can see them on your screen compared to our moon. So they are fairly large, and each one is a unique world with an interesting story to tell us. And well, it's graduation season. Maybe some of you are getting yearbooks about this time. And so in yearbooks, you know, sometimes you've got these superlatives, things that describe people in your school. And we can do that for the moons here too. I thought that might be fun, a fun way to remember what these planets are like, or these moons are like. Like our own moon, you might describe it as most likely to meet an astronaut. That's already happened 12 times. Or it might be the most likely to hit your eye like a big pizza pie. It's a song. Ask your parents. Now, for the moons of Jupiter, some of the superlatives we might use to describe them include, for the closest of these large moons, Jupiter, Io, it's the most volcanic. For the next one out, Europa, that's one that we really want to try and take a spacecraft to and land on. We think there might be an ocean under its icy shell. For the next one out, Ganymede, we might call that one the big moon on campus because it is the largest moon in orbit around Jupiter. It is also the largest moon in the entire solar system. It's actually larger than Mercury is. And then for Callisto, I've given it the title of most craters because it wouldn't be nice to just call it old. It has a heavily cratered surface. We think it's the oldest surface in the solar system. For planetary scientists or geologists and An old surface is something that hasn't been reprocessed by, plate tectonics, something like that. And we think a lot of moons, like Europa, it's being reprocessed by its ocean, the shell breaking apart and shifting. Io with its volcanoes, it's being resurfaced all the time. But Callisto, not so much. So all of these very interesting moons worth studying, but they aren't alone. There's an even larger collection of moons here around Jupiter. It's a big planet, lots of moons. Let's take a look at all of them, but instead of seeing all of the moons individually, let me just show you how they move around Jupiter. These are the orbits of all of the moons in orbit around this planet. If you want to count their orbits, you should get up to 79. Well, that's a lot. And with a group that big, we should be able to look for some patterns. That's a pretty important part of science. So let's see. Let's get a little farther away here. All right, well, the computer is helping us out. I think I see a pattern, though. Some of the moons go around Jupiter in one direction. As we're viewing it here, it would be counterclockwise. And then there's another set of moons, mostly the more distant moons, that go around the planet the opposite direction. I've got the ones going around counterclockwise colored green. The ones going around clockwise are colored red. Now, of course, we've come up with a special way to classify these orbits in science, and the way things move is one of the many scientific rules that follows something called the right-hand rule. And you can see what the right-hand rule is with your own right hand. So if you can make a kind of a fist with it, stick your thumb up. If you're looking at, say, a planet, your thumb would be the North Pole, and then your fingers would wrap around in the direction the planet spins. So if you look down on the Earth from above its North Pole, the Earth spins counterclockwise. The same thing is happening for these moons. Those closer moons to Jupiter, we're looking down from above Jupiter's North Pole here. They're going around the planet in a counterclockwise direction. But farther away, the moons are going backwards. And of course, there's a special word for that too. The moon's going around counterclockwise in this view. We're going the same direction Jupiter rotates, the same direction Jupiter moves around the sun. Those are prograde orbits. And the ones going around backwards are retrograde orbits. You've probably run into that word retrograde before, but that's what it means in astronomy, something going the opposite direction from usual. Now, there are even more groups we can break these down into, and we think that each of these groups is important too. They all have different colors on your screen now, especially among those retrograde moons. The more distant ones, they seem to be in 3 different groups, just kind of based on the size and tilt of their orbits. And there must be a reason that we can group them together like that. There must be a reason that those moons form such interesting groups. And so astronomers are hot on the case there. They're trying to figure it out. And we may be able to figure it out too if we move on to our next target. Let me just take a quick check here. Well, I don't have anything in the inbox just yet. So I'm going to go ahead and plot a course for our next destination. Let's head on out to Saturn. Now, to get out to Saturn, we are going to roughly double our distance from the sun. So we're a little over 5 astronomical units now, and we're going to jet on out to about 10 astronomical units. Now, when we get there, we aren't going to see Saturn right away because I want to get down to the bottom of this moon puzzle first. So I'm going to put the orbits of all of Saturn's moons on the screen. And if you count these real quickly, the first things you'll notice is that there are more of them here than there were around Jupiter. Saturn is known to have 82 moons at the moment. And similar to Saturn, we can break them up in the same kind of way. We've got a bunch of prograde orbits going around clockwise from above the North Pole, colored green again, and a bunch of retrograde orbits going around the other way. Now, unique here at Saturn, we've actually seen one of these backwards moons, one of these retrograde moons up close. When the Cassini spacecraft was approaching Saturn before going into orbit, it flew right by this moon, which you may have trouble seeing because it is one of the darkest objects in the entire solar system. Its name is Phoebe. I'm going to try and get it against the Milky Way in the background there, so you can maybe pick out its shape just a little bit better. But we do have some decent pictures of Phoebe, and Cassini was able to tell us some interesting things about it. Although most of its surface is very dark, there were some brighter patches that suggested there's a lot of ice inside this moon. And that has led some planetary scientists to think that the moon perhaps formed somewhere else in the solar system, maybe much farther away, maybe even outside the orbit of Neptune. But then something pulled it into the inner solar system. Maybe it was the early days of the solar system. There's still a lot of gas and dust around that helped this little object change its orbit. Maybe it was wandering around the gas giants, just happened to get too close to Saturn and to get captured as a moon. But whatever happened, it looks like it has suffered some collisions, either along the way or since becoming a moon of Saturn here. In fact, there is a huge dusty ring that goes all the way around Saturn that we think is dust that was ejected off of the surface of Phoebe. Let's try and get to the bottom of that. But along the way, as we get closer to Saturn, let's take a look at some of its other moons. So again, a lineup comparing some of the moons of Saturn to our own moon. Phoebe is actually that little one right next to our moon. Then we've got Enceladus, famous for having big geysers that erupt off of its south pole. I've got Tethys and Dione right next to that. And then Iapetus and Rhea, a little bit bigger, and then finally Titan, the largest moon in orbit around Saturn. All of these moons have interesting claims to fame. Rhea might have its own little ring system going around it, or may have at one time. Iapetus, it's kind of hard to see on the screen right now, but it's got kind of a two-toned surface. One side of it is very dark. One side is bright white, and that's because maybe moving through that big dusty ring that is coming off of Phoebe. So all these moons are related, and they might all be related to, that big ring going around Saturn. That is probably Saturn's most obvious and striking feature here. You may have noticed a thin ring when we were at Jupiter. All of the gas giants have them. But the ring here is much brighter, much easier to see. So you may have even seen it through a little telescope. Pretty good sight. I highly recommend it. And let's get a little bit closer to the rings and see what's going on there. They're pretty broad. They stretch all the way around the planet, thousands of miles across, but they aren't very thick, so I can almost make them disappear on your screen there. And if we dive in a little bit closer, you can see there's just lots and lots of little bits of stuff, little bits of dust and ice, a whole lot of ice here. That's why they're so bright and so easy to see. All right, so we've got more moons here than anywhere else. We've got bigger and brighter rings here than any other planet in the solar system. What's going on with Saturn? What can it tell us about the other gas giants in the solar system? Well, to answer that, it might help to know just how much stuff is in these rings. They're pretty impressive. They look really big, but how much stuff is really here? We had a question in the post that you may have seen before the video started, and I was curious how much stuff it took to make these rings. I wonder if anybody came up with a good guess. Planetary scientists have been working on this as well, and they got a big hint thanks to the Cassini Spacecraft. The same one that flew by Phoebe. It spent about 13 years in orbit around Saturn. Now it's not here anymore, but it ended its mission in spectacular style. It actually dove into the atmosphere of Saturn, but just before doing that, it completed multiple orbits where it dove between the planet and its atmosphere. So let's see if we can actually see the orbits that Cassini followed towards the end of its mission. Those red lines are the path the spacecraft followed. Now, going between Saturn, the planet itself, and its rings allowed us to separate the planet of separate the mass, how much stuff is in the planetary system, from the planet itself. And that gave us a mass of the rings, how much stuff is in the rings. And it turned out to be, in scientific notation, 1.54 times 10 to the 19 kilograms. If you want to write it out, it just means you move that decimal point 19 points over and it becomes a really big number. Now, for comparison, all of the water on the surface of the Earth is 1.87 times 10 to the 21 kilograms. So the entire mass of the rings of Saturn is a tiny fraction of all of the liquid water on the surface of the Earth, which is especially impressive when you see just how big the rings are. I've added a little model of the Earth off to the left-hand side there, and that thing with a circle around it on the right is a model of our own moon. So not just sizes to scale, but also the distance between the Earth and the moon. So you can see Saturn, with its rings, fills up most of that 250,000 miles between the Earth and the moon. And yet those rings that wrap all the way around Saturn are made with a tiny amount of water. Relatively speaking, it turns out to be about the same amount of water as there is in the Arctic Ocean. So not even one of the big oceans like the Atlantic Ocean or the Pacific Ocean. A relatively small amount of water on planetary scales is all you need to make those giant rings. So it shouldn't be so surprising that we can see rings around lots of objects in the solar system. And I think that relatively small mass of the rings of Saturn, for me, is one of our possibly surprising facts of the day. Those numbers are pretty impressive to me. Let's see. Oh, looks like we've got an important message here. Something about the rings. Shannon asks, the rings are wide, but why are they so thin? Good question. So a lot of things in space end up in big flat rings because of one scientific rule called the conservation of angular momentum. And it's something that happened early on when we looked at the formation of Jupiter. And the same thing is at play here. And the same thing is about to make an appearance in just a moment. So conservation of angular momentum does a couple of things. First, if you've got a disk, something flat, a lot of individual elements that are rotating around, it's going to cause the disk as it rotates to flatten down. So that's why in the early solar system, everything was a big flat disk and all of the planets kind of go around the sun on the same level. And so the same thing has happened here. A lot of these moons going in orbit around Saturn, and all of the little bits of dust in the ring, they're all orbiting around Saturn, and so they've all gotten flattened down into this flat disk. So even a lot of the moons, I know my extra Earth and moon are kind of stuck on the screen too. But you can see some of the other moons of Saturn there. They're bright dots rotating around. They're all kind of lined up with the rings. It actually goes right around Saturn's equator. So that's part of it. And something that you'll be able to see in just a second is that all the gas giants also rotate faster than the rocky planets do. And part of that is because the gas giant planets are bigger. And as the gas giant planets pulled in more gas and dust, they grew bigger and bigger. As that stuff stuck onto the planet, their orbital momentum had to go somewhere. So it helps speed up the rotation of the planet. So rings either around planets or around young stars, or even our own galaxy, are big and flat because everything is rotating, and you have to follow that scientific rule, the conservation of angular momentum. Let's see, another question about Saturn before we move on. Ben asks, how old is Saturn? Well, we think Saturn was probably the second planet to form in our solar system, not too long after Jupiter. There's some pretty cool things that probably happened early on. Jupiter was probably wandering around through that disk, and it may have been Saturn that actually helped Jupiter settle into the orbit it's in today, and explains lots of other things that we may actually be able to see next week. So Saturn is probably similar to the age of the universe, some 4.5 billion years. Now, before we carry on here, do want to also mention one more cool thing about Saturn, and really all of the planets in the solar system, that conservation of angular momentum, that spinning that everything does, has another interesting effect here. So it's flattened out the ring a lot because it's lots of small particles. But for the planet itself, this spinning has also had a cool effect. I've added a perfectly spherical cage around Saturn. And if you look real carefully, right around Saturn's equator, right under the rings, that cage actually touches Saturn's cloud tops. But take a look at what's going on at the poles. There's a lot of empty space. So that conservation of angular momentum, that squishing, has flattened the whole planet. So although, as the International Astronomical Union tried to tell us at the beginning of the show, all planets in the solar system are round, they aren't all the same degree of round. A lot of the planets are kind of squished down. In science, we call that measure oblateness. And so Saturn would be the most oblate planet in the solar system, or if you'd like, the least round planet in our solar system. And if you didn't like the big numbers about the rings, I think being the least round planet is also another possibly surprising fact of the day. So there's something else you can spread around. The next time somebody asks, just tell them Saturn isn't as round as it could be. It's kind of like you take a ball of pizza dough, you spin it, toss it up in the air, and it gets squished down too. So the same thing is happening to planets. Pretty impressive, if you ask me. All right. Got one more item in the mailbox here we haven't cleared out. Before we move on, yeah, I've been throwing a couple of words out almost interchangeably, but we have a question. What's the difference between a planetary scientist and an astronomer? I've said both. Yeah. Does it matter? Well, it depends on who you ask, I guess. You could draw some distinctions. An astronomer would be, well, in one sense, kind of a big catch-all term. So just about anybody that studies something in space is a kind of astronomer. But just like there are lots of kinds of biologists, one kind of biologist might study just mammals, or even more specifically, just ape species. The same thing happens in astronomy. So you can be an astronomer and you can study stars. You can be an astronomer and you can study galaxies. You can be an astronomer and just study how things move in the solar system. Or you can be somebody that really focuses on the actual physical objects, the planets, the moons, how they form, what shapes their surfaces. And it's that last case is really a planetary scientist. You're looking at what the planets are all about, how they form, how they change and evolve. So that's really the difference. But big picture, they're all kinds of astronomers. But planetary scientists would be more interested in the processes that make solar systems and the worlds in them. So hope that helps out. All right, let's see. Let's make sure we knock out the last couple planets on our list. We still got a couple to see, but these will be pretty quick because they are virtual twins of each other. And we're going to see a lot of the things that we've already seen, so we won't get into too much detail here. Our next destination is, of course, planet number 7. This is planet Uranus, and once again, we're going to basically double our distance from the sun, so go from 10 to about 20 astronomical units. Now, a couple of things to mention about Uranus right away. It is kind of a medium-sized planet in the solar system here. One of its most famous attributes is that it is tipped over on its side. I've added a blue line in the background there. That's something called the ecliptic. That's the path that the sun appears to follow in our sky. It's kind of the Earth's orbit stretched out across the entire sky. And it's kind of one way to look at a medium plane of the solar system. And all of the planets are tilted relative to their orbits, or tilted compared to our orbit, the ecliptic. And you can see little models of all of the planets on the screen, and all of them are being displayed with their tilts compared to the ecliptic, and also their rotation rates. So I mentioned that the gas giants rotate faster before, and you can actually see that on the screen now. But most of the planets are relatively upright on their axis. They aren't tilted over too far, except for Uranus. It's actually tilted more than 90 degrees. It's kind of laying over on its side. So that causes some wild seasonal variations on the planet, and it can kind of get easy to confuse day and night and years at times, but that's probably a subject for another day. But just that tilt by itself is an interesting feature. What explains it? Well, like most of the real odd things in the solar system, like, Venus basically rotating backwards, or the kind of fuzzy interior of Jupiter, it's probably a giant collision. That's kind of our default in planetary science to guess that it was a giant collision that caused this really strange thing. But of course, they're working hard to model how that may have actually happened, and to make sure that really does explain what we see. Another interesting feature here would be, the size of the planet. All of the planets just appeared the same size on your screen. But let me put Uranus in context here. We were moving around with models of the Earth and the Moon during last week's show. But since we're talking about gas giants, let's use the Earth and Jupiter. And you can see here that Uranus kind of fits in the middle. This is truly a medium-sized planet in our solar system. You've got Earth. All the rocky planets are smaller than Earth. You've got Jupiter and Saturn, just a tiny bit smaller. Then Uranus and Neptune are kind of in the middle. And I'll see that when we reach the end of our journey today. Then we've got rings here, like we had rings around all of the gas giants. And I think the discovery of the rings here are kind of an interesting story. Now, I've tried to recreate it on the screen for you as best I could, but it's really hard to recreate the story because it actually took place in the 1970s using a telescope mounted in an airplane. You don't hear many discoveries made that way. But for the rings of Uranus here, astronomers were actually watching something called an occultation. It was predicted that the planet would move directly between the Earth, or in this case, where the airplane was flying in the Earth's atmosphere, and a distant star. And when it did that, of course, the planet would block the starlight. If you watch that happen very carefully, you can learn things about the planet's atmosphere. But as it happened, as astronomers watched, before the planet actually blocked out the star blinked out a couple of times, and then it blinked out because of Uranus, and the star blinked out a couple more times. And as I drift away from the planet, if you watch really carefully, get that screen close to your face. No, be safe. But you may notice some of the stars in the background blinking out there. It's hard to see on the screen right now. But the only way that astronomers could explain this was if a ring existed around the planet. You had these occultations happening before the planet passed in front of the star, and the same pattern in reverse after the planet passed by. I know it was really hard to see on the screen, so if you weren't able to see it, I've recreated the effect on a very large scale. So just watch Uranus here, and I'll move something in front of it. There you go. There's an occultation. So there's what astronomers saw that helped them discover the rings around the planet. Speaking of things that go around the planet, just like the other gas giants, there are a bunch of moons here, 27 altogether. Slightly smaller moons overall here. There is Uranus's larger moon, Titania, compared to our moon, as well as another one, Miranda. Now, this moon I really want to highlight because images from the Voyager 2 spacecraft when it flew by in 1986 revealed a moon that really looked like it had been broken apart at some point. Believe it or not, we think it was because of a giant collision. And then it reformed later on. So is it possible that collisions between moons are relatively common? I already tried to blame collisions for maybe the groups of retrograde moons around Jupiter and Saturn. And around Saturn, we can also blame collisions perhaps for the rings themselves. The low mass of the rings might also be related to their age, although Saturn is pretty old. The rings might be much younger, perhaps 100 million years old instead of 4.5 billion years old. And by analyzing the orbits of moons here around Uranus, we think that some of these moons are doomed to collide in the future. It may have happened to Miranda or Miranda's parents in the past, and some of these moons may collide again in the future. Let's see. The brighter pink circles looks like they're kind of on opposite sides of Uranus on our screens here. Those mark the moons Cupid and Belinda. And by analyzing their orbits, astronomers think they are going to collide in the next 1,000 to 10 million years. So not a very fine prediction, but somewhere in that window. Then the darker pink circles, these two over here, we'll try and get them front and center. Those two circles are around the moons Cressida and Desdemona. There's some hints about the interesting naming history here if you look up those names, but astronomers think that those moons may collide in the next 1 million years or so. So perhaps what we see at Uranus today is not the planet's original family of moons. I'm sure Uranus has had moons for most, if not all of its history, but because they're pretty tightly packed in here, maybe they've gone through multiple cycles of collisions, forming vast rings, and then among those rings, new generations of moons form, but they're pretty close together, so they collide again and form a new collection of moons. So collisions might be an incredibly important part of the ongoing evolution of our solar system, forming and destroying and reforming moons around the gas giant planets. Pretty interesting stuff. All right, getting down to the wire here. So let's get down to one more planet. Just a couple of things to show you about Neptune. I've already mentioned that it is a virtual twin of Uranus, so let me prove that to you. I put that cage around Saturn earlier to show you how squished it was, how oblate it was. Here at Neptune, I'm just going to show you how close it is in size to Uranus. So the cage is the size of Uranus. You see Neptune down below. Pretty close. Let's see. We've got, of course, the planet itself. We've got rings and moons going around it. One more quick callback. An old message in my inbox asked what the most recent planet discovered was and who discovered it. Now, assuming we mean in the solar system, that was certainly Neptune. And so I want to show you a little bit about the discovery of this planet. It goes back to the late 1700s when the planet Uranus was discovered by William Herschel. When astronomers figured out how it was moving around the sun, they found that it wasn't always exactly where gravity would predict it would be, at least if you only took into account the gravity of the sun and the other planets we knew about. So a couple of mathematicians took a crack at predicting where another planet might be. These mathematicians, these theorists, are John Couch Adams up above and Urbain Le Verrier down below. Now, they both made predictions for where another planet might be. And Le Verrier actually sent his predictions to a German astronomer named Johann Galle, and he found it on the first night of his search. So he found it pretty quickly. The prediction wasn't perfect, but it was close enough. And that revealed the planet Neptune to us in the year 1846. So that was the most recent planet discovered, at least as we define planets today. Like we've already seen, Neptune has rings around it. It's an interesting gas giant with a thick atmosphere, lots of storms. But since we've been focusing on moons and things, let me show you a couple of the moons here. Neptune has 14 moons in orbit around it, and two quick stories here because I can't help myself. I've shown you how important collisions might be for moons around these gas giants. Let me offer a counterpoint for you. Two of the moons in orbit around Neptune are called Naiad and Thalassa. And now I'm showing you moons in kind of an interesting way. We've locked on to Thalassa, front and center, and it kind of orbits right around Neptune's equator. And then right next door is the moon Naiad, and its orbit is tilted just a little bit. Now, that could be a recipe for disaster. You might think that these moons would collide, like some of them we've seen around other planets. What has happened here instead over millions or perhaps billions of years is these two moons have gotten themselves into a special resonance, a special orbital relationship where every time Naiad approaches Thalassa's position, Naiad has always separated itself just a little bit, so they never collide, and both moons are able to survive right next door to each other this way. I don't know, a little bit of celestial social distancing. Gotta keep just a little bit of space between each other for safety. So that's a good lesson there. And one more interesting lesson here at Neptune, and a preview of coming attractions, is Neptune's largest moon, Triton. Triton is a pretty big moon in terms of the entire solar system. It's in the top 10 in the solar system. It's only a tiny bit smaller than our own moon. I'll show you that when we arrive. But two other strange things about Triton. Its orbit is a little bit tilted, like the outer captured moons we've seen around other gas giants. It is also retrograde. It's also going around Neptune backwards compared to what we would expect. That is a recipe for a captured moon. So the thinking is that the Triton formed somewhere else, perhaps beyond the orbit of Neptune, and it wandered too close to the planet, became a moon later on in its life. Now, we're going to talk a lot more about things out beyond the orbit of Neptune in a future episode. That episode with Pluto 2 weeks away. Next week, targeting the other small objects in the solar system, I'm going to talk about asteroids. If you've seen any of our shows in the Dome, you may already know that is a topic near and dear to me, and there are a lot of really interesting ones in the solar system. So that one should be a pretty fun show. I already have a lot of really neat stuff, at least in my opinion, planned out for that one. So, of course, I recommend tuning in. All right, we had one more message come in, I think last one for today. Let's see, this one comes from Charles. Is there gravity on Saturn? What about the other planets you talked about today? Interesting question, Charles. Yes, definitely gravity on Saturn. Everything in the universe, and certainly then everything in our solar system, has a gravitational pull. Gravity is just it's a trait of anything with mass, anything that is made of matter, made of stuff. So Charles, you have a gravitational pull. It just happens that you are much smaller than the Earth. So the Earth's gravitational pull controls you and holds you on the surface rather than you dragging the Earth around. So yeah, Saturn has gravity. And in fact, Saturn is much more massive than the Earth, so its gravity is much stronger. That's how it's able to hold on to that huge collection of moons. Neptune's got gravity. That's how it's able to hold on to moons like Triton. That's how it captured Triton. The Sun's got gravity. That's how it holds all of the planets in orbit. So yeah, certainly gravity is another one of those things that is kind of found all over the universe, and it'll be an important part of all of our stories. But I got more stories to prepare for you. So again, next week, next Thursday, tune in again for our next episode. Again, asteroids, the topic for next week. We'll be back again thanks to our sponsorship from Allianz Partners. And I just have one more special message for you this week. It's something that we saw earlier in the show. It's one of the moons we saw at Saturn. Now, we didn't get to see it up close, but of course, Enceladus, I mentioned, it's got these plumes erupting from its south pole, these giant geysers that actually form another ring around Saturn. So it's spreading its material all around the Saturnian system. And until next time, the best thing that I want you to take away from the show is that if at all possible, please don't be like Enceladus. Be safe out there. Take care of yourselves, and hope to see you next Thursday. Thanks for tuning in. We'll see you again on our next journey through the cosmos.